To complete our system of governing equations for the torsion of round bars, we're going to also need a material constitutive laws. And let's go ahead and start simple, and we'll go ahead and assume an elastic stress-strain response. And note that there's only one strain in the system, that's the gamma z theta, and so the relevant constitutive law for linear elastic isotropic materials then is that the shear stress in the system, so the gamma z or z theta is connected to the shear stress sigma z theta via the shear modulus g. So sigma z theta times g equals gamma z theta. And that actually completes our entire system of equations. We have now a constitutive law, and by convention, when we just have one shear stress, we usually just call it tau. And we'll go ahead and draw out the subscripts because there's only one shear strain also. So we'll say tau is equal to g gamma. And that's basically the exact same place in the theory as sigma equals E epsilon had in the theory for deformation of bars with axial forces. So if we list it all out, that's our first equation is our constitutive relation. We have our kinematic relationship, which says gamma is equal to r d phi dz. We have the equilibrium equation, dt dz plus little t equals 0. And we have the connection between the resultant torque, capital T, and the shear stresses, which is the integral over the cross-sectional area of r tau dA. So this gives us our complete theory. We can look at it or count it up a little bit and make sure that it is complete. The variables in the theory are the rotation phi, the shear strain gamma, the shear stress tau, and the internal torque capital T. So there are 4 fields, unknown fields that had to be solved for in general to determine the mechanical response. And if you look at it, we have the same number of equations as we have unknowns, so we have a complete theory here. Couple of things to keep in mind about the theory is, first of all, that the rotation field, phi of z, is constant on each section. So there's just one value per section. That's why it's only a function of z. It doesn't depend on radial position at all. And similarly, the internal torque T only depends on z also. So there's just one value per cross section. But more complicated than the axial force problem here is that the shear strains have a variation on the cross section, and in particular they will be linear on each cross section with respect to the variable r. The shear stresses will be linear times the modulus of variation on each cross section. So if g depends on the radial position, then tau will not necessarily be linear anymore. But if g is a constant, so if you have a homogeneous system, then tau will actually be linear on the cross section also, just like the shear strain.